Our next speaker is Dr. Shailesh Nayak. Dr. Nayak serves as the Secretary to the Government of India for Ministry of Earth Sciences. He received his PhD degree in geology. He is a versatile person with a distinguished career and proven track record of 29 years at both space and ocean-related services. Dr. Nayak was the president of Indian Society of Remote Sensing, and he was the president of ISPI's Technical Commission 4. He has represented ISRO as the International Ocean Color Coordination Group and International Global Observation Strategy Coastal Theme. He will present to us tsunami warning system for the Indian Ocean. Let's welcome Dr. Nayak.
Thank you very much. I'm indeed honored and privileged to be here and to talk to this august gathering. I would like to say specifically my friend Kohei to invite me to this conference. The tsunami, as we know, is a series of ocean gravity waves, and last decade, or last couple of, we had three major tsunamis: Sumatra, earthquake, and Chilean, and very recently Japan. And we all know that what tsunami can do. It can destroy a large amount of installations on the coast. A lot of lives can be lost. And what we have been able to do with the development in science and technology, I would like you to present. The reason is that, especially the Indian Ocean, we did not have any tsunami warning system before 2004. And of course, we had very efficient tsunami warning systems in Japan, run by Japan Meteorological Agency, and PTWC Pacific Tsunami Warning System, run by NOAA US. This, what I'm going to present is how the system has been developed in the Indian Ocean. As we know that the tsunami travels very fast. It travels almost at a jet speed in the deep ocean. It has a very low amplitude in the deep sea. Almost you cannot even recognize that tsunami is there. But when it comes to the coast, it becomes tens of meters, maybe 10, 20, 30 meters high, and the wavelength can be several hundred kilometers. And the most important thing about tsunami, we must remember that it does not lose energy as it travels from the source to the coast. And that is the reason we see large amount of destructions. The most tsunamis are created by the earthquake, but it is not uncommon to have a tsunami by volcanic eruptions and landslides, and it can also be because of the meteor impact. The most of the warning systems can take care of the earthquakes. We do not have very efficient system to take care of the other causes for the tsunami. So in this, what we have is basically two important things. One is the how to detect the tsunami getting earthquake, that's the one thing, and how to monitor and find out change in the sea level which can occur because of the tsunami. If you look at the Indian Ocean, the energy which is released in the Java, Sumatra, Himalayan, Alpine belt is about 20% of the flow. The most of the energy which is in the Pacific Ocean, about 75%. And we had the 6 major tsunamis in the Indian Ocean, which last 3 centuries. And you can see that roughly we have about 2% And the most tsunamis which has a very slow rupture velocities, these are the most dangerous because it lasts long and ruptures long areas, more than 1,000 kilometers or so. And this is one which creates the havoc. And Sumatra was something like this, which created havoc in the ocean. Now, there could be three. Of course, there are different classifications, and there are different 9 tsunamis. But for the most practical purpose, there are 3 major types of the tsunami. One, which is a very low, what we call as a local tsunami, which generates within the 100 kilometers of the source region, and which has about less than an hour travel time. For such tsunamis, there is no much time for the warning because it travels in 15, 20 minutes or 30 minutes. But of course, the effect is also not very severe. And this kind of tsunamis we have been seeing generating on Japan, Indonesian coast many times. The second is the regional tsunami, which can generate a tsunami wave in about 1,000 kilometer radius and can reach between 1 and 3 hours. This is one can cause a lot of destruction. But the most important and the most destructive is the distant tsunami, which can originate more than 1,000 kilometers away and can have a travel time more than 3 hours and can cause a widespread destruction, not only in the nearby vicinity, but entire ocean basin, like in what happened in Sumatra or what happened in Chile. Professor Shunji Murai was mentioning that after 22 hours, they received a small tsunami in Japan. So these are the distant tsunamis, and the most critical to detect and warn the people who are in the coastal regions. Now, to do this, there are different components of the system. The first, most important, that we must have a system of seismic stations to detect the earthquake and whether it is tsunami or not. The second is we need to put the bottom pressure recorders to measure the sea level changes. This should be as near as possible to the fault zone. Then we need to have a tight gauge network on the coast to monitor how the tsunami is moving. There are other new things that are coming, like the coastal radars have been found to be extremely useful to detect the incoming waves. But of course, this we can do in somewhere around 300 kilometers or so. And of course, you need certain upper ocean and other observations as well, because there could be other activity happening which could also affect us. The other important thing is the very solid communication network to get all the information, scientific data in real time, and to provide the advisories. Also, we need a modeling of the propagation and generation, propagation and inundation of the tsunami. Also, we need data on the bathymetry, coastal topography, the vulnerability, and of course, all this together, we need to build a system for the education and research, and this is what we call as a tsunami warning center should have. I will try to explain each component. Now, I thought that we will try to highlight, because this is on the remote sensing conference, what remote sensing and GIS can do in such kind of a system. Actually, there is a lot of, and especially the geospatial technology, especially GIS, help us to acquire, display, and analysis of the real-time data, all seismic sensors, sea level changes, as well as to organize the scenario database. I'll come back what exactly is the scenario database for the assumed earthquake parameters, their retrieval, display, and analysis at the time of the event. Large amount of bathymetric and topographic data is collected, and today the most topographic data comes from the high resolution satellite as well as the platforms. The next is the decision support systems, which allows you to code the entire standard operating procedure and these are the areas where remote sensing and GIS play a very crucial role. And I would like to acknowledge my association with the ISPRS between 2004 and 8 helped immensely to build the tsunami warning system. We have a large amount of seismic stations, of course, our own Indian stations as well as the international stations. The important thing that we must have about 8 stations in the radius of about 900 kilometers, and the data should come within 30 seconds or so. This is the most crucial requirement, and many times we use the various means to get the information fast enough to process the data. We have been analyzing now something around 300 stations data streaming in real time to the warning center and these processed. We can realize that the kind of infrastructure required to process large amount of seismic data, and we should be able to do within 5 minutes. The other important thing is the bottom pressure recorders, and this is very important because it should be placed not too near to the fault zone or not too far from the fault zone. And this is placed at about 3,000, 4,000 meter depth, and it can detect a change in the sea level as small as 5 millimeters. So it's a very highly sensitive instrument, and you can see that what happens during tsunami. Normal curve, and it is programmed, the algorithm is built in this, so it has this normal movement is already programmed. Any change occurring in this, it will get triggered and it will give you the signal that how the tsunami is going to change, or what kind of level of the tsunami. And this is a very complex system. It looks very simple, but it's a very complex system like this, where you have a buoy which is anchored, and this is the bottom pressure recorder which is left, and it communicates with this with the acoustic signal. And this is very important because the acoustic signal is greatly dependent on the salinity and the temperature changes. So you must be aware that what kind of changes are expecting, and it should be within the buoy should not go too away from this, so that it always is a communication. And this normal case, it takes about 15 minutes one data to release. But when the tsunami occurs, it's programmed in such a way that it gets triggered on its own, and then it starts sending data every minute to this, and then from here you can send data through satellites or any other system which you can set up. So this is a very complex system, and it's very important that where exactly you place them. The second is the tidal gauge network. This is also very important because not only the other international stations, like this, it can give you the idea whether your simulated data is working well or not. And it can also provide a signal which is indicative of a tsunami. And this is being used many times. Like Indonesian stations will give you idea that what kind of tsunami is likely to come to the Indian, because there the tsunami which is much faster. So this is how it is being done. There is a lot of talk about the satellite altimeter, because satellite altimeter also measures nothing but the sea level. And during the 2004 tsunami, there was 4 altimeter data was available. This was processed and found that it does contain the signal of a tsunami. Only issue is today that the processing of altimeter data takes a lot of time, and it's not easy to do it within few minutes. If you can do within few minutes, probably it would be quite useful to monitor the tsunami. There is another major use which we use the altimeter data is to test and validate our simulated models, because you do not have the entire ocean, we do not have the tidal stations or bottom pressure recorder to validate. While altimeter can give you the basin-wide